Thank you for giving me the opportunity to summarize in my own mind what has happened in the last 8 years. So 8 years ago, Sylvan Klebsch, this guy over here, came to Imperial College with a vision about a new language that would make a better job of concurrency and concurrent programming. And I thought, come on, it's just, there is nothing new to find there. It has all been invented, but I was wrong. So a following was created around this idea. Sebastian Blessing, who disappeared, he suggested that we should implement the language, and he went immediately and he worked on the distributed version of the language. We implemented the language. There is now, as for any serious programming language, you can you have got a page with all the material that exists, and you have got a GitHub page with all the versions, and by now there is a community which also controls the language development. You can also find the examples that I'm going to use at this location. And there is a playground for you to try things out. But what I want to discuss today is the main ideas that drove the language. So the goals for this programming language was that it should be concurrent and support also distributed programming. It should have a very efficient implementation, and it should be easy to write correct programs. So what do we mean? Concurrent. There should be one driving paradigm, and the driving paradigm is the actor paradigm. Efficient, there shouldn't be locks. You shouldn't need to use any locks, and the runtime should also not be using locks. You should be able to share state without making copies. And easy to write, should be data race free, data log free by construction. It should be safe for you to create object cycles as opposed to Rust. There should be some simplicity in the model when you program. So you have got this figment of atomicity in your mind, which I'm going to talk about, and causality, which I'm also going to talk about. So first question, is the language indeed efficient? 4 years after our first excitement, and after we started the project, we tried to run benchmarks in order to find out, in particular, how does the language compare with respect to garbage collection. And we created a couple of very basic micro benchmarks. And here we are reporting how Pony behaves. It says Orca, but the reason it says Orca is because the garbage collector is called Orca with respect to Erlang and with respect to Java. And in Java, we're using C4, which is the best garbage collector there is. And the results are tremendous, so we were super happy because we were faster with any of these. And the benchmarks, we have been honest. We just wrote small benchmarks, and we compared, and we found these wonderful results. So we were extremely happy about that. On the other hand, on the other hand, here we are so here we have been measuring the performance for 4, 8, 16, 32, 64 cores. And here we have been measuring footprint. And on the other hand, in terms of footprint, there is one example where Pony performs awfully. We have not been able to devote as much time as we would have liked to benchmarking, but then we revisited the whole question a couple of years later. And we have got a paper in Agere from this October. So what we decided we should be looking at a benchmark suite that has been developed by others, not us. And the benchmark suite that we used is Savina. And Savina has been proposed as a good benchmark suite to compare actor-based languages. So in this benchmark suite, there are 32 programs, and they are already implemented in Akka. And we have asked our friends to implement them in CAF, and we have compared. So here is one example from the parallel benchmarks. And you see that Pony is the green guy and doesn't do very well. Aka is the red guy and does best, and Kaf is the blue guy and does pretty good too. But then in the sieve of Eratosthenes, Pony does much better. And then after we had 16 programs and we didn't know what to do, we computed the average, and Pony is not doing super good with a low number of cores and is getting better. On the other hand, for the concurrent story, Pony is doing pretty much here. For this example, is doing not as well for this example, and overall is doing better than everybody else. So the jury's out. These are all micro benchmarks, and we are trying now to develop a benchmark to rule them all, where you can tune and get more interesting results, but this is work in progress. So this is what we know about efficiency. I would say it is encouraging, and it is not final yet. So, however, one big company has decided to choose us because of efficiency. They are major contributor to the Pony endeavor, and they have developed their own distributed version of Pony. Now, Pony, as any serious programming language, has several interesting features, but I'm going to just talk about a couple of those. And today what I want to discuss is actors, causality, some aspects of the type system, and how the type system has been used for garbage collection. Actors. So can I have a show of hands who knows about actors? Should I skip it? OK, so I should go very, very fast. The asynchronous messages are called behaviors, or rather the response to the asynchronous messages. In Pony, as opposed to, say, Erlang, the actors take the first message out of their queue, and we have got also synchronous messages. And Pony is an extension of the object-oriented paradigm. So here is an example of an actor in Pony. It has got two local variables, two fields, name and environment. This is the constructor, and it has got a behavior. When it gets poked, then it asks the environment to print its name. And here is the main program that creates three actors and then pokes them. So execution could look as follows. The main program creates the three actors. And then let's look at what happens when we poke. When actor is poked, then it asks the environment to print its name. So the main program sends the messages poke, and then those messages send print message. Sorry, those behaviors send print messages to the environment. And it is possible for the print message from A to arrive last, even though it was sent first. And it is also possible for the print message to arrive first, even though here it arrives last. And it is possible for poke to arrive here, but for the behavior not to be scheduled until later. It's all concurrent programming. And finally, it is possible to have times where the behaviors are, where the actor is idle and doesn't execute any behavior. So next point is causality, and the reason for this is that now we have seen there is some element of uncertainty in the program. For instance, here we have got four actors. I indicate the actor through this rounded square that is the name of the actor, and that is the thread of the actor, and these are the times when it is executing a behavior, when it's active. So the question is, what do the other actors do while I am executing my own behavior? Do they go and they modify the world, and then I will be affected by that? When will the messages arrive, and when will they be taken off the queues? So this uncertainty is alleviated through types and through causal message delivery. What do types do? What they do is they give you the following guarantee. They say when a message is taken off the queue any changes to the world will be invisible to you. So the other actors may execute and modify the world, but it's not the part of the world that you can see. And this guarantee holds actually upon message sent. As soon as the message is sent, anything that is in the world that is visible from that message is essentially unmodified until the receiving actor can start and work with it. We'll see more about it later. The other reason that this uncertainty is alleviated is because we have causal message delivery, and this goes beyond the guarantees that are given, for instance, in Erlang or in akka. So there are different definitions of what causality means. And I want to first give an example. So let's assume we have got a scenario where there is a customer who decides to go and buy stuff, but before they buy stuff, they need to make sure that they have got enough money in the bank. So what do? There is a behavior run, and they go and they determine what is the price of what they want to buy. They go to the bank. They send a message to the bank saying, credit me with the price so that I'm sure I have got enough money. And they send a message to store that says, buy from me something with a particular price. And store and bank are fields in the actor and in the customer. The store then knows about the bank, that is his own field, and when the store receives the message buy, it asks the bank to debit the customer with a particular price. And what does the bank do? It has got a table, a map from customers to their balances. When it gets created, it initializes the table. When it receives the credit message, then it increments the balance for the particular customer. And when he receives debit, it checks whether there is enough money. And if there is not enough money, then it goes and complains at the Bank of England, makes a big fuss, otherwise makes the payment. So we are hoping that this big fuss will never happen. But why will it not happen? So from the point of view, the simplistic point of view, when the customer runs, it wants to be sure that credit will arrive at the bank before debit. But we said that there are the guarantees that are made about the queues are weak. The fact that somebody sends something before somebody else is not necessarily a guarantee. So the question is, could it be that the debit overtakes credit, and then indeed the Bank of England is going to make a fuss? And luckily the question is no. And why is it no? The guarantee of causal delivery is the following. First, what does it mean for a message to cause another message? Either I receive a message and then I send another message. So if I receive message M and then send M prime, then M is a cause for M prime. And if I send M and then send M prime, then M causes M prime. And causality is transitive. And what we have as a guarantee is that the message arrives at one queue, at the same queue in causal order, not across different queues, because that is too distributed and difficult, but at one queue they all arrive in causal order. So in particular, when we worry about this, we know that because the customer sends credit and then buy, then credit causes buy. And because the shop receives buy and then sends debit, buy causes debit. Therefore, credit causes debit, and therefore credit is a cause of debit, and therefore it arrives first. No worries there. Right, so now, is that an expensive feature to have? It is dirt cheap if we're working on one node. What about distributed programming? And the guarantee that we have is that if we organize everything in a tree topology, if all the communication goes through through a tree, then message delivery is causal. So no matter how the customer, the bank, and the shop are organized in that tree, we know that we have causal message delivery. The other subject that I would like to discuss is how uncertainty is alleviated through types, and talk about the type system. So there is a paper in Agere in 2015, and I'm going to go briefly through what the type system offers. So the very, very interesting thing with the pony type system is that the types reflect execution. For every interesting operation that affects the topology in the heap, there is a corresponding operation in the type system. So the question that we need to answer is, I have got a reference, I have got a path that gives me access to some object. This path can be just a variable, or a variable and a field lookup, or a variable and a field lookup, another field lookup, and so on and so on. So I have got a reference to an object. What can I do with that? Can I read? Can I write? Then the next question is, if I have an alias, if I create a new alias to the reference, I create a new path that gets me to the same place where the old path gets me. What can I do with this new path? Can I do everything that I could do with the first path? Then what do I do if I drop a reference? If I remove an alias to an object, can I do now more things? What if I read a field from my reference? I follow the path. And what if I remove, if I extract a field? I take I overwrite the value of a field in an object. Now the object that was the old value of the field has got one less path to it. What can I do with that? And the answer is, what can I do with my reference? We have got the concept of reference capability, which we call kappa. If I alias my reference, then there is an operator on the reference capability, which is the kappa the exclamation mark. I have made one more reference to the thing. Unaliasing is the dash. I have removed the reference. If I read a field from a reference, if the reference had capability kappa and the object has a capability kappa prime for the field, then the ensuing reference is this viewpoint adaptation. And if I remove the reference, then it is the extracting adaptation. So these are the operators, and this is the backbone of the type system. But because I want to also talk about garbage collection, I'm going to concentrate on this, and I can talk offline about that. So the reference capabilities. The reference capabilities, they are attached to a reference, and they express whether the holder of that reference may read or write the object. But they also express whether other aliases to the object may be written or read, and distinguishing actually whether the other references are local or global aliases. And I want to discuss what this local and global alias mean. So assume that we have an actor of type this actor, and it has got a field called other actor that points to some other actor. So this is the diagram to understand that. Then I also have got another field, holder, and holder is initialized so that it points to some object of class account. So this gray blob is an object of class account. Then I'm executing a function, And this function declares a local variable called local alias, and local alias is assigned holder. So the holder is one reference to the account, and local alias is a local alias to the holder. It is a local alias because it comes from the same actor. Then I execute a behavior. I call the behavior take on the other actor, and I pass the holder. So now the other actor also has got a reference to the account. So this is my current alias, the holder. This is the local alias and the global alias. And the capability that I give to the holder needs to be, oops. So the capability that I give to the holder needs to be so that it respects what the local alias can do and what the global alias can do. The more this one can do, the less those two guys will do. If, for instance, this one is allowed to take the account and give it away, then this one should not be able to read it. If this one is only allowed to read, then all those should also be only allowed to read. So, in more details, in Pony we have 6 reference capabilities, but I'm going to omit transition because it is a little bit of an edge case, and I want to get the main idea across. So the question is, those capabilities, what rights do they give to the holder, the local alias, and the global alias? So the ISO capability and the ref capability say the holder may read and write. The val and the box capabilities say the holder may only read, and the tag says the holder cannot do anything. Interesting background story. When Sylvan started thinking about these things, he only had this in mind, but because we set it up in a nice matrix, we realized that there is one more, and which is the tag, and actually it is very useful, this one more. So now let's look at the local aliases. Well, the local aliases need to be somehow different for these two and for these two, since the holder had identical rights. So the ISO capability says the local alias is not allowed to do anything, cannot read, cannot write, can only know the identity of the thing. Whereas the ref says the local alias might read, write, whatever they want. The val capability says the local alias is only allowed to read, while for box it says, I don't know, it's actually a union type. And tag, well, we don't know. The local alias might read, write, we know nothing. The global alias now, since here locally, at least one reference is able to write, then the global alias is not allowed to neither read nor write, otherwise we would have data races. Here, since we want to be sure that we can read, then the global alias is also only allowed to read, and here the global alias is also allowed to read. The other question is, which of those can I send across actors? And the answer is I can send ISO, because I know that I'm the unique one who can read. So if I give up my ISO and I give it to Justin, then I know that nobody's going to be in trouble. I can also give val, because I know everybody's in agreement, only nobody's going to read from it, so it can be shared across. And I can give a tag, because when I give it as tag. I say, you are not allowed to look inside it. So the interesting story is tag comes up a lot when you have lookup tables and things like that, when you only want to pass the identity to somebody else who has got the rest of the information locally. Right, so the reference capabilities, they are attached to the references, which are paths, things like x.f, x.f.g, when we're looking up more fields, and they express whether the holder is allowed to read or write, and say something about the other objects. And also note, that not only do we have capabilities for variables and arguments, we also have got capability for the receiver. So here we are saying this function is modifying the receiver, therefore it needs a ref capability for the receiver. So I'm going to go very fast through some pony code. We have got here a person who has got identity and strength. When they eat, their strength increases. We saw that function already by some amount that is taken from the food. And the take a bite function from food decreases the calories and returns parts of the calorie. And here in the main actor, we have got an apple variable. Then we have got a pear variable. They are both food. Laurie and Jan are people, and they eat the apple and the pear. And if we look at the problems, here we see that I am modifying the calories, and therefore, the function take a bite should have a ref receiver. Here we are calling take bite, and which requires the food to be a ref, but here it is a box, so we need to change it. Okay, so this was a short and fast description of what the type checker is doing. Now I would like to concentrate on the main and wonderful contribution of what do these capabilities really mean. So what we have here is, again, two actors, A1, A2. Here is the timeline of the actor. We progress through time, let's say this way. Sorry, here is the activation of the actor. Forget about time. This is a snapshot. So here is actor A1, A2, and here is what the actor has access to. So the actor A1, you can imagine, has got a local variable of type ISO that points to that object. And this object 10 now, so all these round guys here are objects 10, 12, 13, 20, and so on. And I'm indicating through the black arrows the references that come from one object to another object through its field. So we can imagine that here 10 has got some field, I don't care what it's called, but this field has got a reference capability, and this field is pointing to 12. And 12 has got another field that has got a reference capability that points to 13, and 13 a box that points to 12, and also a ref that points to 10. So this is a topology that is possible through when I'm using those capabilities. Now, what does the topology mean? The ISOs introduce a partition of the mutable heap into disjoint regions. So these turquoise triangles indicate the objects that belong to the same region. And we see that there are 4 regions. One starts at 10, the other 20, the other 30, the other 50, because they are all they have got all an ISO pointing to them. Moreover, there is one immutable region, and these are the blue objects, and it's indicated through this light blue square that is not very visible here. And these are introduced whenever I have got a val capability. So from 12 to 10, I have got a val capability, and I know that everything that is reachable from 100 is going to be immutable. So all the objects here are immutable. And then with this approach, I can have my cycles, as I have got them here, and I've got them here, which I couldn't have in Rust, and which are nice to have when you want them, and you don't need to start worrying about unsafe programming. Then we also have that there are no incoming pointers into the mutable region. So 21 cannot have any kind of mutable reference to 12. It could have a tag reference, but I'm excluding it here in order to tell my story. 21 cannot have a mutable or even box reference to 12 because it would go directly inside somebody else's region, and 13 cannot point to 12 because, sorry, 13 cannot point to 20 because 20 is an ISO and there is only one distinct entry into a region. And then what we see is there is at most one actor at a time that has got any kind of access to the objects in a mutable region. So here A1 has got access to the objects in that region and in that region, and A2 has got access to the objects in that region and that region. So A1 can go in there and create more objects, modify objects, change what they're pointing to, perhaps even do garbage collection, and nobody else is going to be affected by that. And A2 can do the same. And they can both go inside the blue region and read stuff, but since all that is immutable, it's going to be safe. So what we have is data race freedom by construction. The type system makes sure that we don't have any data races and we don't need to log, we don't need barriers, we don't need anything. The type system does it all for us. Now, how do we do communication? We want to be able to pass data around, and ideally we would like also to be able to pass mutable data. So remember, there is this requirement at most one actor at a time has access to a mutable region. And that means that a val reference can be sent safely to any other actor. So it is totally safe to send the object 100 to actor A2 because it's an immutable object and there are no restrictions about access to the immutable region. You can go and read anything you want as often as you want. What about the mutable stuff? So I can give up a reference and then I can send it to another actor. For instance, I might want to give up the reference that goes from 32 to 50, and then it is safe to give it to A1. I still have got my guarantee. At most one actor has got access to a mutable region. And similarly, I might want to give up my reference to 30 and pass it to A1. We have got the guarantee of data race freedom. So what that means is we can share mutable state without copying and without any data races. So what guarantees does the type system give me? It gives me no data races because at most one actor has got access to a mutable object at any time. Immutability is deep and permanent. So as soon as something is in the immutable region, it remains there. Stuff can move from the mutable to the immutable by giving up capabilities and turning ISOs to val and stuff like that, which I'm not going to go. But everything that is in the mutable region stays there. Everything that is reachable from there is immutable. The capabilities become weaker with the distance. So if I have got a long path that has got that is allowed to write with W, then every shorter path of it is also allowed to write. And we have got this figment of atomicity that says if upon message receipt, an actor sees an object at a certain capability that is read or write, then if later on the contents of the object is different than what it was when upon receipt, then it was I who made the change. So it means I cannot observe anything that changes because of other actors. Any change is due to me. So the semantics that we have for behavior execution is interleaved. So let's say A1 is executing a behavior, and then other actors execute, and then he continues with his behavior here. This is one behavior. And A2, his behavior is broken into 3, A3 it's broken into 3. But I, as a programmer, I don't need to know any about this. I can believe that all my behaviors are atomic. This one will finish on its own, this one will finish on its own, and so on, or any other order, but without the interleaving. So that simplifies the programming model. So the last thing I want to talk about is garbage collection. And it came as a surprise to me how important garbage collection is, but it is super important. Perhaps I don't need to say it here to you. There is Doug Lee, who is the master of concurrency and also garbage collection, talking about the issues that arise. And in Pony, we have got a garbage collection protocol that is based on ownership and reference count. And we have Juliana, my PhD student, found the wonderful name Orca for it. So what's so great about Orca? There are a couple of papers that where you can read about Orca. Here we describe how it works and some of the benchmarking that you have seen already. Here we describe the model that makes sure that it works, and it was actually surprisingly difficult to make the model and fun. And here we describe another protocol that has to do not with the collection of objects, but with the collection of actors. And I can talk about this one offline. So the wonderful thing about the garbage collection in Pony is that it is fully concurrent. There is no synchronization, no locks, no barrier, no stop the world, no nothing. Wow. So here's the way that I like to explain it to myself. We have got the actors, and again, this bit is behavior of an actor, and here is where the actor is idle, and here behavior, and another behavior, and the actor idle, and the black blobs or the black squares is where the actor executes garbage collection. So the interesting thing is that at this point in time, this actor is executing the behavior. He's doing garbage collection. He's doing behavior. It can be fully concurrent. So this is what the model says. But we wanted to have experimental evidence that indeed this is what is happening. So Juliana has been instrumented execution on a 4-core machine. And for each of those cores, she could record whether at some time the core was executing behavior, was executing sending or receiving of messages, or executing garbage collection. And the time goes like this. So you can see, for instance, this part here is magnified here, and we see that this actor is doing behavior, receiving behavior, and then GC, while this actor is doing sending, receiving behavior. This is doing GC. It is indeed fully concurrent. So what are the challenges, and what have we done about them? First challenge is who collects the object. Second, how do we avoid data races between garbage collector and mutation, garbage collection and behavior? After all, the garbage collector needs to go and trace the object graph. It needs to find what is accessible from the frame or from the fields in an actor. And the mutator goes and modifies that at the same time. Okay, so the answer to who collects the object is the allocating actor. So whoever created an object is the owner, and he is responsible to collect the object, to find out when the object is no longer accessible and to remove it. Now, given what I have been talking about so far, you know the answer to how do we avoid data races between garbage collection and mutation, or between tracing and mutation. And this is the type system. How does the owner know whether there are foreign references to its own objects? How does the owner know whether other actors are interested or have a path to their object? And here we have got a scheme where the owner keeps reference counts for all the objects that the other actors are interested in, and also a reference count for the objects that he's interested in. And when these things are modified, he goes and notifies the corresponding actor. Now, he goes and modifies means send messages. And here we do have the problem of what happens if one message overtakes the other message. There are increments and decrements messages, and we need to know that the decrement messages do not overtake the increments. But we have got causal message delivery, so it all works. So we have got a case where there is a very tight connection between the language design and the runtime system, and to my knowledge, this is totally novel. There were schemes already where the type system was helping the garbage collector, but they were not as intricate, because all you knew is that there was some domination graph, and as soon as you remove a link from the dominating link, you can remove everything underneath. But here we can have a much more fine-grained garbage collection, and we don't rely on the regions anymore. So I'd like to outline roughly what is happening. Here there are 3 actors. This actor owns 11, 12, and 13. He has created all these objects, but notice that he doesn't have any links, any paths to those objects. But for instance, actor 2 is interested in 11, 12, 20, 21, and 23, and therefore those objects should not be garbage collector. So the challenge is that the owning actor might not have paths to its live objects, but the objects are still nevertheless live. And there are cycles potentially in the object graph, and cycles are problematic with garbage collector, with reference counting garbage collecting. But please remember, the reference counting is the number of the actors who are interested in something, not the cycles, not the number of references within the heap. So roughly what happens is that the owning actor keeps an upper bound on the number of actors we have got a path to the owned object, and it collects the object when this number is 0. The foreign actor, the actor that does not own the object, keeps count of the reference to unowned objects. So this actor A2 needs to remember that it's interested in 11, which it does not own. And when the number of references to unowned object changes, then it needs to notify the owner. So when an actor receives a message, it receives objects with a message, so this number of references changes, so it needs to tell the owner. When it sends messages that also change, it needs to tell the owner, and also when it does tracing and it discovers that it does not, that it's no longer interested in an object, it tells the owner. And what we have is now a system that is sound and complete, which means we remove eventually, we remove all the dead objects, and we only remove dead objects. So here is again our evaluation with respect to Erlang and Java using C4. And we have distinguished between the mutator time, the overhead of the mutator, the concurrent GC, and stop to the world step, which works very well. And remember, footprint is not that great. And the other thing that we measured is responsiveness. So we measured the difference. We ran a different benchmark where we did a bunch of a sequence of requests, and the requests were some Fibonacci calculation, something like that. And we measured the difference in completion time between subsequent such requests. So this is jitter, or we think it is. And we saw that in the case of Orca, the jitter is very low. In Erlang, it's higher, and in C4, it's even worse. So this is, again, another indication that things are very encouraging. So, as a summary, we have got several features in the language. I'm happy to talk afterwards more, or if you ask me questions. There is a large group of people who have contributed. Some of them were at Imperial College, but there are several people outside and several people on GitHub whose identity I do not know, but they have got funny symbols, and it has been a very interesting and rewarding journey for me. Please have a look at the language. Thank you.
Questions?
From an architecture point of view, how do you decide what's an actor and what's an object?
An actor is something that can execute concurrently, whereas the object is passive. The actor is something active. So I did not have that problem when writing code of determining when something should be an actor. I have been writing some code in Verona, and there I had the problem of when is something a resource. And I don't know why I didn't have the problem. Do you have an answer?
No, it's just
But I think the things that execute concurrently are actors. So when we looked at the Savina benchmark suite, it was immediately clear what should be the actors, even without looking at the code of written in the other languages.
Thanks a lot for the great talk. I'd like to know a little bit more about Project Verona. I realize that's a whole other talk, but
that's a different talk. Ask me afterwards.
So, I mean, these look like really useful capabilities to have. How come you decided to put them into a new language rather than maybe into a library for an existing one? So I'm thinking particularly of the type system.
One would have, if you put them into a library, you would need to make sure that the whole language follows the library's type system. So it's a very invasive change. Plus, then the runtime system relies on the capabilities.
I've tried a little bit of my own with the Pony language. One thing that keeps catching me out is the fact the garbage collection doesn't run during a loop.
Yes.
What's the reason for that?
That's a very good point. The reason is totally an engineering reason, that it is easier to trace when you know where when all you are interested in is the fields. You don't run garbage collection during a behavior. You only run it between behaviors. That means that you only need to trace from the fields of the actor. If you were to trace during a behavior, then you need to walk the activation, the frames of the activation stack, and find at which location is which object of which type. And moreover, if anything has been inlined, it's even more work. So from the point of view of the protocol, nothing changes. From the point of view of the engineering, it's a hell of a lot more. Yeah. Yes. we have come across that problem too.
I mean, building a new language and a community around it is, I mean, I think you sort of gave the impression that wasn't what you were expecting to do, but has it been a rewarding and interesting thing of its own to do that?
Yes, I was not expecting it to happen because when Sylvan came, I thought there's nothing much new to discover, and there was, and it has been wonderful to get into touch with so many people who were interested in it, and my own students worked on parts of the compiler. We then experimented with other features, like, for instance, how do we do object initialization in Verona, path-dependent types. So all sorts of things that theoretically are interesting and somebody else does, now they become super urgent because they have to be in our language. Yes, it's a great thing to be doing. Yeah. Thank you. I think it's 15:15 and everybody needs to go and have a real break now. Thank you for
Thanks so much.
Thank you.